A 4 mm thick aluminium sheet of width W is equal to 100 mm is rolled in a 2-roll mill of roll diameter 200 mm each. The workpiece is lubricated with a mineral oil, which gives a coefficient of friction mu is equal to 0.1. The flow stress sigma of the material in megapascals is sigma is equal to 207 plus 414 epsilon, where epsilon is true strain. Assuming rolling to be a plane strain deformation process, the roll separation force F for maximum permissible draft is use F is equal to 1.15 sigma bar into 1 plus mu L by 2 H bar into WL, where sigma bar is the average flow stress, L is the roll workpiece contact length, and H bar is the average sheet thickness. Let's look at the solution. We know the value of thickness of the aluminium sheet, which is T is equal to 4 mm. We have the width of the aluminium sheet as W is equal to 100 mm. We have the roll diameter capital D as 200 mm, and that gives roll radius R is equal to 100 mm. We have the coefficient of friction mu is equal to 0.1, and the flow stress of the material sigma is given as 207 plus 414 epsilon megapascals. Roll separation force F is also given as F bar is equal to 1.15 sigma bar into 1 plus mu L by 2 H bar into WL. Then the maximum possible sheet reduction due to rolling is delta H max can be written as mu square into R, and delta H max is nothing but the initial thickness minus final thickness, that is equal to mu is 0.1 square into R is the roll radius, which is 100. So substituting the initial thickness of the sheet to be 4 mm and finding out the final thickness of the sheet after rolling will give us 3 mm. Now the average sheet thickness is H bar is equal to H naught plus HF by 2, and that turns out to be 3.5 mm. The contact length of the workpiece L is calculated as under root R into delta H. R is equal to 100 and delta H turns out to be 1, and the contact length of the workpiece will be 10 mm. Due to the rolling operation, the workpiece will experience the strain. Therefore, the true strain experienced by the workpiece is epsilon is equal to natural log H naught by HF. H naught is the initial thickness of the sheet before rolling, which is 4, and HF is the thickness of the sheet after rolling, which is 3. And the strain experienced by the workpiece will be epsilon is equal to 0.287. The average flow stress can be written as 1 by epsilon into 0 to epsilon sigma d epsilon. Let us consider this as equation 1, and the flow stress given in the question is sigma is equal to 207 plus 414 epsilon megapascals. In general, the average flow stress is usually represented as sigma is equal to sigma naught plus k epsilon power n. Comparing these two equations, we get sigma naught is equal to 207, k is equal to 414, and n is equal to 1. Sigma average will be is equal to 1 by epsilon into sigma naught plus k epsilon power n into d epsilon. Simplifying that will give us sigma is equal to 1 by epsilon into sigma naught epsilon plus k epsilon power n plus 1 by n plus 1. Now we have sigma is equal to sigma naught plus k epsilon power n by n plus 1. Sigma is equal to 207 plus 207 into 0.287, which is the strain experienced by the workpiece. We get the flow stress as sigma is equal to 266.53 megapascals. Therefore, the roll separating force experienced is F is equal to 1.15 into 266.53 into 1 plus 0.1 into 10 by 2 into 3.5. Simplifying that will give us the roll separating force as 351 kilonewtons. The accepted answer range for this question is 340 to 360.